In the world of comic books, there's one substance that can bring the Man of Steel to his knees: Kryptonite, a glowing green rock from his destroyed home planet. It's a classic piece of fiction. But what if I told you that in 2004, geologists drilling in Serbia stumbled upon a mineral whose chemical makeup was almost identical to the kryptonite described in the movies? This isn't fiction. This is the story of Jadarite, the real-life kryptonite, a substance that doesn't weaken a superhero, but holds the power to fuel our entire planet's future. It all started in the Jadarite Valley of Serbia. Geologists from the mining giant Rio Tinto weren't looking for superhero weaknesses. They were on a routine exploratory mission. Deep beneath the earth, their drills pulled up a core sample containing a mineral no one had ever seen before. After analysis, it was officially named Jadarite in 2006. Here's where it gets strange. The chemical formula for this new mineral is sodium lithium boron silicate hydroxide. Now, think back to the 2006 film Superman Returns. In one scene, Lex Luthor examines a piece of kryptonite, and the label on the case reads, "Sodium lithium boron silicate hydroxide with fluorine." The real-world mineral matched the fictional one almost perfectly, with the only difference being the lack of fluorine. The coincidence was so uncanny it made headlines around the world. Of course, Jadarite doesn't look like its cinematic twin. There's no ominous green glow. It's a rather plain, dull, earthy white powder. But if you put it under ultraviolet light, it gives off a faint pinkish-orange glow. Its true power, however, isn't in its appearance or its fictional connection. It's in its chemistry. Jadarite is packed with two of the most critical elements for the 21st century: lithium and boron. Let's talk about lithium first. Lithium is the magic ingredient in the rechargeable batteries that power our modern world. It's in your smartphone, your laptop, and most importantly, in electric vehicles. As nations around the globe race to ditch fossil fuels and switch to electric cars to combat climate change, the demand for lithium is exploding. It has become one of the most sought-after resources on the planet, often called white gold. The Jadarite deposit in Serbia isn't just a minor find. It's one of the largest lithium deposits ever discovered. The proposed mining project there aims to produce around 58,000 tons of battery-grade lithium carbonate every single year. That's enough to produce batteries for over 1 million electric vehicles annually. This single discovery could significantly impact the global supply chain and accelerate the green energy transition, especially for Europe, which currently relies heavily on importing lithium. But Jadarite is a double whammy of value because it's also a rich source of boron. Boron might not be as famous as lithium, but it's a quiet workhorse of modern industry. It's used to create high-strength, lightweight materials. Think about the enormous blades of a wind turbine. Boron helps make them strong yet light enough to spin efficiently. It's also crucial for producing heat-resistant glass, like the Pyrex dishes in your kitchen, and advanced ceramics used in everything from electronics to armor. Farmers even use boron compounds as a micronutrient in fertilizers to improve crop yields. Finding a single mineral that contains high concentrations of both lithium and boron is incredibly rare and makes the Jadarite deposit exceptionally valuable. So how do you find something like this, buried deep underground in a specific valley in Serbia? You can't just wander around with a shovel and hope to get lucky. This is where the fascinating science of applied geophysics comes in. It's the art of seeing the unseen, of creating a map of what lies beneath our feet without digging a single hole. Geophysics uses the principles of physics to explore the Earth's subsurface. Let's break down some of the key techniques they use, which are like a doctor's tools for examining a patient, but in this case, the patient is the Earth itself. First, there are gravity surveys. This technique is like weighing different parts of the Earth. You might think gravity is constant, but it actually varies in tiny amounts from place to place. These variations are caused by differences in the density of the rock below. A massive, dense body of rock will exert a slightly stronger gravitational pull than a basin filled with lighter, less dense sediments. Geophysicists use incredibly sensitive instruments called gravimeters to measure these minuscule changes. In the case of Jadarite, it was found in an ancient lake basin filled with relatively light volcanic and sedimentary rocks. A gravity survey would have shown this area as a gravity low, a red flag telling geologists that this basin structure was worth a closer look. Next up are magnetic surveys. Just like gravity, the Earth's magnetic field isn't uniform. Different rocks and minerals have different magnetic properties. Some, like the mineral magnetite, are strongly magnetic and create distinct spikes or dips in the local magnetic field. To find these, geophysicists fly airplanes or drones in a grid pattern over an area with a magnetometer trailing behind. The data creates a magnetic map of the subsurface. This map doesn't point directly to a mineral, but it reveals the underlying geology, faults, folds, and the location of volcanic rocks. Since Jadarite formed in a basin with volcanic ash, mapping these volcanic sources and the basin's structure is a critical clue in the hunt. Then we have seismic surveys, which are basically an ultrasound for the planet. The process involves generating powerful sound waves at the surface, usually with a specialized thumper truck that vibrates the ground. These sound waves travel down into the earth, hit different rock layers, and bounce back up. A series of receivers, called geophones, listen for these returning echoes. By measuring the time it takes for the waves to travel down and back, scientists can create a detailed, cross-sectional image of the rock layers, almost like a slice of cake. This is invaluable for understanding the architecture of a sedimentary basin, identifying faults that might have acted as pathways for mineral-rich fluids, and mapping the overall structure that hosts a deposit like Jadarite. Finally, there are electrical and electromagnetic surveys. These methods work by probing the Earth's conductivity, how well the ground conducts electricity. Different minerals have vastly different electrical properties. A massive deposit of copper ore, for instance, is highly conductive and will light up like a beacon on an electrical survey. These surveys work by either passing a current directly into the ground or by generating an electromagnetic field at the surface which induces currents below. While Jadarite itself isn't a massive sulfide conductor, these techniques are still incredibly useful for mapping the different rock units within the basin and identifying zones of chemical alteration that are often associated with mineralization. So, putting it all together, how did this geophysical detective story play out in the Jadar Valley? Rio Tinto's team started with a regional assessment, likely looking at existing geological maps and satellite images. They knew that these Miocene-era basins in Serbia were promising for boron, which was their initial target. They likely then flew airborne gravity and magnetic surveys over the whole region. This gave them the big picture, outlining the basin's depth and structure and flagging anomalous areas. Based on those results, they would have moved to the ground, employing more detailed surveys like electrical or seismic methods in the most promising spots to refine their understanding. This entire process, from regional maps to detailed ground surveys, is about narrowing down the search area from thousands of square kilometers to just a few high-priority targets. The goal of all this expensive geophysical work is to answer one question: where should we drill? In 2004, they drilled one of those targets, and the core they pulled from the earth contained Jadarite. It was the confirmation that all their geological and geophysical detective work had led them to a world-class, one-of-a-kind mineral deposit. Since that first hole, over 400 more have been drilled to fully map out this immense resource. The story of Jadarite is a perfect example of how modern exploration uncovers resources vital for our future. While the proposed mine has faced significant environmental concerns and local opposition, a critical and complex part of any modern mining story, the sheer potential of the deposit is undeniable. It also proves that valuable lithium deposits can exist in geological settings we hadn't really considered before, outside of the typical salt brines and hard rock pegmatites. The discovery has kicked off a new wave of research, with scientists trying to understand the unique conditions that created Jadarite so they can find more like it elsewhere. Applied geophysics will be at the heart of this continued search. As technology advances, our ability to see into the Earth with greater clarity and precision will only improve, allowing us to find the resources needed for a sustainable future. The real-life kryptonite may not have the power to stop a superhero, but with its vast reserves of lithium and boron, it truly has the potential to empower a global energy revolution.